I will begin. And we're talking canaries. Dearly Father, we thank you for this day, and I thank you for this class. It's opportunities to meet together and study topology. Help us to learn a little bit more today about it. In your name, Lord Jesus. Amen. So, as I have written, we are studying. Listen, good job. Okay. Topological quotients. Now, so the first idea is this idea of an identification. And you have to be careful. The words here, they're slippery. A continuous, so it's a continuous surjection, all right, is called an identification if the open sets of Y, all right, are precisely those subsets of Y which the inverse image of is open in X, all right. So, okay, so that's an identification. All right. Let me make sure that that was the email I'm hoping it was. Yay. All right. Secretaries are awesome.
Still teaching 450?
Yeah, I'm teaching 450. I was asking the secretary to make me copies of an old test so we could work on it. All right, so as he mentions here, F inverse commutes with complementation of sets. So a continuous onto map of Y is an identification if and only if closed sets in Y are also those of the form C subset of Y for F inverse of C closed in X, and conversely. So in other words, you could also say if and only if the closed set of Y are precisely the subsets A of Y such that the F inverse is closed in X. You could measure identification by closed sets just the same. And so if you have a continuous map, all right, we define saturation. Let's see here. So F from X to Y, continuous. Then what? A subset of X is saturated by F if what? If whenever X is an element of A and X is an element of A, okay, and Y is an element of X, okay, and F of X equals to F of Y, then what?
Well, it's an element of A.
Right. So in other words, if the image of F hits some point twice, both of those images must be coming from this subset A. Because it's a glare, stupid light. I need to get some like fluorescent lights or something. All right.
So A has to be the inverse image of F of A.
Whoop. Oh, you're right. So equivalently, it has to be, which is to say that, what is that to say?
Well,
So-
it's that F A has to be the inverse image of F of A.
So yeah, A has to equal to F inverse of B for some B for some subset, right?
Yeah.
He says, saying that F as an identification amounts to saying the open sets of Y, all right, are exactly the images, FA, of saturated sets A. All right, let's look at this example. Look at his example. If I do well today, we'll cover the first 2 sections, okay? If I do really well, we'll cover the first 3. Which probably means we'll cover the first section.
Have more faith in yourself.
Example. Ooh, that's a nice blue. Let A be a cover of X, all right? And consider the disjoint union Y. So his symbol for disjoint union is this. So it's like a union, but with I guess you can, it's kind of like a square union with some, I don't know what you want to call it. It's like somebody took SpongeBob and
Upside down pie.
put him through a guillotine and flipped him over or something. I don't know. Let's see here. Disjoint union of A. I mean, we see what we want to see, right? A such that A is an element of A. A. Disjoint union is a thing which has frustrated me at various points because people use it without constructing it, but to construct the disjoint union, you have to do something like, for example, the disjoint union of R and R, right? So everyone knows that R union R is R again, right? Disjoint union of R and R is not R again.
Is it the empty set?
No, it's a new thing which has 2 copies of R in it which are not the same.
Oh, okay.
So it's not R2 though, is it?
I think it's R2, yeah.
Oh, it is. Okay.
Yeah, I think it's basically R2. Now there's a careful. I hope that's right. I don't know what else it would mean. Goodness gracious. There's a careful description of how you actually form the disjoint union using set theory. I'm not sure if it was in here or in Moncrief's. I was reading about it the first week I was preparing to teach you guys, and I was going to say something about it. And then somehow I got lost in the madness of the semester. Where's that thing? Yes, I know, I'll use the index. Fine.
So what's the advantage of this disjoint union again?
Oh, it's a way of constructing things.
42.
I mean, you want to say you have 2 copies of the same space, right?
Yeah.
But you don't want them to be the same space.
Why doesn't you just use the cross though? Like the,
That is a question. Why not just use the Cartesian product?
Yeah.
Disjoint union, page 42 is where he defines it. Example 3.10, let xi, I and element I be a collection of topological spaces. Consider the disjoint union. And the course's topology among these containing topology of each xi. Topological space defined in this way is called the disjoint union of the topological spaces xi. I don't know, that's a good question. How does this get us anything that wasn't already gotten to us by Cartesian product? Tell you what, I'll think about that and try to get back on it.
sorry to distract you.
No, it's okay. It's my own. I'm the one who started this. I'm trying to self-fulfill the prophecy that we won't get through the sections I said. Anyway, so disjoint union of this. All right. Where was I? He says the natural map y to x is continuous. Y to what x? Onto an identification if and only if A is an identification cover. So what would the natural map be? We call it F. So F of Y equals what? I don't know if this example is that helpful for us today. We'll eventually find something heavy enough to keep this book open. Haha, another book. All right. It's just y again. The point is, like, so it's, I gotta say this, like, you could have a space that looked like this, right? As 4 pieces, A1, A2, A3, A4. Well, the disjoint union of these things this disjoint union is, it's, think of it like, I mean, that's not, man, I guess you could think of it this way. I'm not sure that that's actually right. Because I asked the same question you asked, which is why not just use Cartesian product, if that's what you mean.
And is the disjoint union a subset of X?
Oh, that's the thing.
Is it maybe the possible combination?
That's the thing. The thing is that they're not. It doesn't give you 4 tuples.
It gives you.
It gives you a thing of 1 tuples. I mean, it's like. Oh, that wasn't smart. Well, anyway, what chalkboard am I going to use it on anyway? Oh, that's right, my chalkboard. So it's more like. Let's see here. To illustrate this idea better, maybe this A2 goes over here, like that. So it's like you'd have A1 sitting there, and then you have the A2 also sitting there. I don't know how to. You have the A3 also sitting there, and you have the A4 also sitting there, like together, but these points aren't the same points over here, they're separate points. So like where this was overlapping, these points in here are now disjoint from those points in the disjoint union.
So they're in a way just they're replicated, like.
It's not a union. I mean, it's something different. I'll have to define this carefully to explain more. But the point is, if you do this, it makes sense, right?
Yeah.
And since everything in X is in some A, as you go over the disjoint union, you hit every point in X. So F is a surjection in this example because F maps onto X because every point in X is in some A, and and everything in one particular A is in the disjoint union of all A's.
Okay.
And that's why he was able to say that it's a surjection, and as he says, it's continuous onto, and it's an identification if and only if A is an identification cover. What was an identification cover? Do you remember that? Oopsie. Skip the camera. Oh man, I'm a little bit. I don't know if I was bad before or not. I may be a little bit off.
It's a cover where a set is open in X if only if its intersection with each element of the cover is open.
I see. All right, I'm gonna move on here. Lemma 5.4. I put my stupid eraser. I hate it. Sorry, I should have skipped that example if I wasn't gonna
It makes sense though, like
properly talk about disjoint unions.
the surjection's easy to see in that case. It's just, I guess, the construction.
Yeah, but the thing that I'm a little bit shaky on, of course, is what I don't have a firm command of what an identification cover was, so that makes the other comment hard for me to understand at the moment. And that's okay. Lemma 5.4, there is something I do want to say to you guys today, so I'll make sure I get to it. Lemma 5.4. F continuous and onto. Continuous surjection. Right. Then if F closed, if it's a closed map, then it's a closed identification. And that just means it's an identification which is also a closed map. And likewise, if F is open, then it's an open identification. All right. All right, let's see if we can think through the proof of at least one of these. Let's look at the second one. Suppose F is open, right? Suppose F from X to Y is onto and open. All right. What do we need to do? We need to show that the open sets of Y are what? Precisely the subsets of Y such that they are, that the inverse image of those sets are open in X, right? All right, so here's his argument. He goes, okay, so first, the fact that it's onto, right, implies what, in terms of set theory? That says that F of F inverse of A is equal to A for any Y, any subset, for any A subset Y. Does that make sense? Does it make sense?
For any A and Y, there is going to be a set that like completely maps to it,
Right.
because it's on two. So, since F inverse of A.
Okay, so you're like,
if you do a double containment, so that's much trouble.
okay, so you're like, if B is a subset of Y, then there exists, let's say C is a subset of X, such that F of C is equal to B.
Yeah. I guess we want to show that.
Which implies that F inverse of B is equal to C.
Where C is going to be a subset of F inverse of B.
Okay.
Other way around. We want to show F inverse of B is a subset of C. Maybe not that it's a. Maybe if we took the union of all such C's, then F inverse of B would be a subset of that.
Didn't you also need 1-to-1 for that over there?
Interesting. Homework. All right. Onto implies that. Therefore, if F is open, right? Let's see if we can understand this at least. If F is open, I'm not casting doubt on the fact that we could prove this. I'm going to go on. If F is, and you may have already said what is needed to prove it, I'm just too dense to understand it at the moment. If F is open, right? What's that mean?
It means that the image of open sets are open sets.
Okay. So if F is open and A is subset of Y is such that what?
F inverse of A is open. Oh wait.
Yeah.
Yeah, then A is open.
F inverse of A is open, then what? Oh. Then F of F inverse of A is equal to A, but this is the continuous image, so this is open, right? And this is an open map, so that means that is open. Which is what we need in order to show that it's an identification, right? The open sets of Y are precisely the ones what? A subset of Y such that they're the inverse image of some open set in X. In this case, just F inverse of A is that open set.
It's 4 o'clock p.m.
Oh, me. Still got some time though. All right. Any questions about? Well, I mean, obviously there's this thing we need to prove, but I'm going to leave that as an entirely. That actually would make a relaxing homework problem. So you guys, I'll let you do that. I don't think that's that hard. But given my current density, I would actually have to go to points and chase points, and it wouldn't be. It would be an end unto itself, and that ironically would be pointless. All right. So he gives some examples here. So your example, F mapping from 0 to 2 pi to S1, where S1 is the unit circle. Okay. And the mapping is particularly, it's defined by f of t, is cosine t, sine t. Okay, that's a familiar map. He says that this is a closed identification. He says it's continuous, and it's onto from a compact set to a Hausdorff space, right? This is compact. This is Hausdorff. Right? Because you can separate points by open sets. I mean, yeah, fine, clear enough. So therefore, F closed. Okay, we had that theorem before. Compact domain, Hausdorff, codomain means. Let's see here, where was I? Lost track. So it's closed, and it's a closed surjection. Oh, so therefore it's a closed identification if we believe lemma 5.4. He then gives you an argument to show that you could prove it's closed directly without resorting to this Hausdorff chicanery. I mean, he gives a specific, you can map 0 pi to the northern half of the circle. You can map pi to 2 pi to the southern half of the circle. And since those are homeomorphisms, you have the union of those two closed sets gives you the whole circle. So the whole circle's closed since it's formed from the union of closed sets under these homeomorphisms. It's pretty nice. Lemma 5.6 is important. Nathan will be sad he wasn't here for this. This is really the lemma that Nathan lives for. I mean, Nathan would like for me to, like the first words out of my mouth this semester have been this, he would have been happy. This is like Nathan's preferred starting point, this lemma right here. Because this is an example of a universal property, which is very categoric in flavor. Lemma 5.6. Universal property of identifications. If we have f, a mapping from x to y, an identification, and g from x to z, a continuous map, all right, there exists a continuous map h from y to z, all right, such that G is equal to H composed with F, if and only if G is constant on the fibers of F. All right, so to say G is constant in the fibers of F, what that means, what's a fiber of F? A fiber of F is something like F inverse of C for some constant, for some C. C and Y. So to say that it's constant on the fibers of F means basically that like G of X is equal to G of Y if X and Y are elements of F inverse of C. Directly, that's what it means, right? That's a fiber, that's constant on the fiber. But what this means, right, when you unfold that, is that F of X
Equals F of Y.
yeah, equals F of Y. Equals C, yeah. So if F of X is equal to F of Y, then G of X is also equal to G of Y. More to the point. All right. And there's a picture that goes with this. You have X, you have G, a continuous mapping from X to Z. Then you have F, which is our identification, down to Y. And then, this is the one that's given by the theorem, H. All right, so here's the proof. So let's see here. Which direction do you guys want to go? Assume the conditions of the lemma and I'll go this way first.
Yeah.
So we have G is equal to H composed with F, where F is an identification, G is a continuous map, right? All right. We want to show G is constant on the fibers of F.
So suppose G of X is equal to G of Y.
Right, so suppose F of X equals to F of Y, right? That would mean that is, right, X and Y are elements of some particular fiber of the F map, right? Then G of X is H of F of X is equal to H of F of Y is equal to G of Y. Done. I am assuming, of course, here that H is a well-defined map, right? The fact that H is single-valued was used here. Okay, I think we picked the easy direction to start with.
Oh yeah.
That's a start.
Yeah, it is a good place to start. If you don't,
I never really like going through something like super complicated and then just like, oh, the other direction's straight on.
yeah, that's a good point. Like don't bury the easy part. Start with the easy part. Throw the student a bone. You know, yeah. I agree. Okay, this way. So assume G G of x is equal to g of y whenever f of x is equal to f of y, right? So now we have to construct this h. How to construct h. So y is an identification, right? I mean, f is an identification. That means that everything in y, right, has the form. If you pick me a point y here, it's equal to f of x for some x. Okay. So if I want to define h, a mapping from y to z, I can do it like this. I can say h of y, right? Now I know that this y is connected to at least one x in the domain, because f is a surjection. And I'm trying to define what h mapping from y to z, right? How do I get to z? I use g. What do I feed to g? X. Now x in principle here is not uniquely given. So this begs the question, is this function well defined? Right? So this could also be equal to what? F of, say, x2, right? So then this would also have to be, you could also say this is equal to g of x2, right? But if that is the case, that's not a problem, right? Because g of x equal to x2 implies what? F of x equals to f of x2, right? But by the way, these are both also equal to the same y. By assumption, I mean, to write, so if I put this y here, and I put this over here, I'm assuming that y is equal to f of x, and y is equal to f of x2. So when I get to this, I mean, when I get to this implies this, well that's not a problem because y is equal to y. I mean, my point is you can show that this is a well-defined map because of that constant condition. Because of this condition right here, exactly. Well-defined meaning that it's single-valued. It still then remains to show what? It's
Wouldn't well-defined be the other direction though? Starting with like...
well, I mean, well-defined, generically speaking, usually speaks to like, when you have an ambiguity of the formula, being single-valued, but we also use this terminology to just basically mean that the domain and codomain of the function are as advertised. That's also part of the definition of a function. There's some disagreement about this terminology, but what were you saying?
No, it just looks like you're proving it's one-to-one.
Well, I guess what I'm trying to say is that there's a question mark here, right?
Because it's not implied that x1 is equal to x2.
Right. What I've written isn't helpful. You have to think about what I'm saying. So,
Yeah.
if you're just looking at what I've wrote, you probably can't make sense of what I'm saying. It's probably bad. So this is the definition, right? If, and they could say something like, if there exists x2 such that, g of x is equal to g of x2. No, other way around, sorry. I don't know, I can't even think of the words to say here, right?
So you assume that like y1 is equal to y2, right? Doesn't look like how you show it's well defined.
y1 equals to y2?
Yeah.
Okay, fine. So h of y2 with y equals to y2, and you're saying y2 is equal to f of x2. So this is equal to g of x2.
Yeah. But y is equal to f of x. So
Mhm.
f of x is equal to f of x2, so g of x is equal to g of x2,
Mm-hmm.
which is it's well defined.
Right. Yeah. I mean, I use this whenever word. That's kind of a. That really means.
Yeah.
Yeah, unfortunate, but true.
Can you go over that like one more time, just really with the well-defined part? I'm not entirely sure what you mean by well-defined.
I've defined h of y equal to g of x.
Yeah.
But the thing is, in principle, if I have y equals f of x, that doesn't have to be for just one x.
Before multiple x's, because we're not trying to show it's 1-to-1.
I mean, to say that it's
Doesn't matter,
surjection doesn't mean it's 1-to-1, right? There could be
Yeah.
different
Yeah.
x's which map to that y,
Yeah.
all right?
Yeah.
So then how do I know that those different x's don't give me a different value here when you feed them to g? Well, I know that because if different x's, because, you know, if the outputs, if f of x1 and f of x, if f of x1 is equal to f of x, then that implies that g of x is equal to g of x2. So that if they are different x's that agree on their image under f,
Mhm.
they also have to agree on their image under g.
Okay.
So there's no ambiguity.
Okay.
It still remains, of course, to show that h is continuous, right? And that is where we're going to need to use some of this business up in here about the inverse image of, this business. So to show h is continuous, what do we need to look at? Like, right? So let U subset of Z be open. All right. And we want to look at, H inverse of Z, right? Of U, rather. But by the way, that is, now H is what? H is, what was Y equal to? I mean, we already have, this is actually essentially building in that G is equal to H composed with F, right? I mean, Y is F of X, so this is true for each X. So, dang it. It's not wrong, it wasn't what I was expecting. Curses. Yeah. I guess, it's not complicated. I mean, he says, let U a subset of Z be open, then F inverse of H inverse of U. So, okay, so he's using the sock shoes formula here, right? Which extends to inverses. So like this, right? Okay, I guess I can. There we go. So this would say that F inverse composed with H inverse is equal to G inverse. So in other words, yeah, F inverse of H inverse of U is equal to G inverse of U. We're trying to show this is open, of course, but the reason it's open is because this is an identification. H is continuous. I don't know H is continuous, do I?
We claim, he says we claim
Oh.
H is continuous.
It is, you can see it immediately because you understand the structure, right? Like, so I'm trying to show this is open, but it's a set whose inverse image
So,
is open because G is continuous.
right, because F is an identification.
Because F is an identification cover, this must be an open set. This convoluted thinking, I tell you, quotient spaces are tough. Anyway, so that's section 1. Dang it. This stuff, and then page 90 is where I really wanted to be today, but I must admit defeat. For I must go confuse other students now. Thanks, guys.